Hartwig Hocker on research related to polymers. He then did a postdoc at Northwestern with Sam Stoop, and then he started his independent career at ETH, where he did his habilitation. And then he's now been at EPFL in Lausanne, and he's going to be telling us about some of his work on essentially self-assembled organic nanowires. Holger.
Thank you, Seth, for this nice introduction. Many thanks also for actually inviting me here. It's been a nice visit so far, and I have to say, in comparison to our own campus that I will show on my very last slide, you have a very, very beautiful campus that is very green. So enjoy this as long as you can, because ours looks a little different. Thanks to everybody for coming. In our group, we do a number of different things. We work on carbon-rich nanostructures. We work on semiconducting devices from crystalline thin films of organic molecules. But the story I would like to share with you today is one specific work we've recently been doing on the relation of structure and charge transport in self-assembled organic nanowires. And if I were not to give a talk about our research, but write a fancy research proposal, I'd probably start this proposal by saying, like, you know, organic nanowires are going to be important as novel types of charge percolation paths, for example, in organic solar cells and the like. But as you probably know better than I do, all attempts to put anisotropically grown nanocrystals or nanowires into devices actually helped to make the performance worse, not better so far. And so the way I see it is that it's more like we need to understand better what happens in the interaction between materials and light, and in terms of charge carrier generation, if the material is confined to nanoscopic structures. And I think that self-assembled organic nanowires might help us in that regard to develop a better understanding. But even for this more fundamental question, I think we still have a long way to go. Typically, synthetic chemists, like I am one, would call any one-dimensionally extended aggregate of a pi-conjugated molecule an organic nanowire, whether it actually conducts anything or not. Yeah? In the better cases, like in this relatively recent elegant example by Tovar, at least they undertake an effort to determine the electric properties of nanowires that they obtained from quadrithiophene molecules substituted with oligopeptides that are reasonably similar to the molecules I'm going to talk about today, as you will see. But even in this case, you know, so in the end they make nanofibrils, but they measure the conductivity of a bulk thin film of microfibers. So the thickness of these fibers is much larger than the nanowires they originally claim. It's been processed from water. There are some strangenesses in the IV curves, and I think that it is fair to say that this molecule conducts. But what is actually the nanostructure that is responsible for conduction, and what is the charge carrier species, is actually not well understood. In this regard, things might be a little better in the case of anisotropically grown crystals, or also polythiophene nanofibrils. However, in that case, I think that it is often the structural understanding that is still lacking a bit. And so what I hope to be able to show you today is that we have a very simple molecular design, so not an over-designed molecule, that forms what we call well-defined nanofibrils, whereby with well-defined I mean nanofibrils with a molecularly defined diameter that have a single stack of the pi-conjugated molecules at their core. And at the same time, the core molecules interact very strongly. And as a result, we see for the first time the photo-induced generation of surprisingly long-lived polaron-like charge carriers in the absence of a dopant. And we can show that these charge carriers are actually responsible for the macroscopic conductivity that these nanofibrils show. So this is kind of the outline of the story I would like to present to you today. And of course, we first have to talk a little bit about the molecular parameters for the self-assembly process, and also the synthesis. So time does not permit me to explain the basic concepts of the self-assembly process that we're making use of in detail. But I can show you at least some general ideas behind it. So here you have an oligopeptide that is a short oligopeptide that is linked to a hydrophobic polymer. So it is known that these short oligopeptides like to align with one another, parallel to one another, and in this way they form tape-like structures such as shown here or here. However, due to the combination of the oligopeptide's molecular chirality and the terminal polymer attachment, the resulting tapes actually twist up into a helical superstructure, and this is what actually laterally limits the self-assembly process. And by means that I cannot explain in detail today, you can actually dial in whether you want to make single tape nanostructures or stack tape nanostructures. And so what we would like to make use of is this kind of single tape nanostructure in order to obtain our well-defined nanofibrils from pi conjugated molecules. And again, something that I cannot explain in detail, the first class of molecules we investigated were actually diacetylenes as kind of model compounds for pi conjugated systems. Why did we choose diacetylenes? Because now we could investigate the nanostructure formation not only by AFM imaging, which gives you the nanoscopic morphology just visually, not only by IR spectroscopy, which gives you a good idea of how the oligopeptides interact with their neighbors via NH-OC type hydrogen bonding. We could in addition also use the topochemical diacetylene polymerization shown here as an additional tool to get an idea about the internal structure and the degree of order inside, because this polymerization, this UV-induced polymerization only works if the diacetylenes are present in a highly ordered and pseudo-crystalline, at least one-dimensional crystalline array. Otherwise the polymerization fails. And so this, if the polymerization works, then this tells you that the internal structure is the same as schematically shown here. And so from the combination of these three techniques, AFM, IR spectroscopy in solution, and diacetylene polymerization, we determined for a matrix of molecules where we varied both the length of the polymer chains and the length of the oligopeptide segments, we determined what are the molecular parameters needed in order to arrive at a reliable self-assembly into helical fibril-like structures the way we wanted it. And as you can see here, it's actually a surprisingly small window of polymer degrees of polymerizations and oligopeptide lengths that are useful in that regard. So this served to then understand the molecular parameters and then transfer them onto the actual pi conjugated molecules, oligothiophenes, paralimbisimids that we wanted to investigate. Before I come to that, however, I'll share with you one little detail that I don't talk about very often because time on a conference talk typically doesn't permit to talk about synthesis, which is a bit sad because, I mean, realistically speaking, my PhD students spend probably more than half of their time doing synthesis, but then it is rarely talked about. The one thing I would like to share with you here is we didn't reinvent the wheel in terms of chemistry. We do standard Suzuki couplings, Stille couplings. We do brominations with NBS. And all standard chemistry. We didn't reinvent any new chemistry. However, we found a very nice way to overcome one of the drawbacks that those of you in the audience working synthetically for sure know, and that is the low solubility of our intermediates and products. They're designed to aggregate or crystallize by pi-pi stacking, and so at the same time that makes them very little soluble. And so my PhD student who was working on the project initially had the idea to use a new very bulky polychlorinated protecting group derived from chlorandic acid anhydride. So there is literally almost no chemistry with this compound. It's been used as a flame retardant. It's produced in kilotons. It's been used as a flame retardant in polymer materials, but it's not been made use of in terms of chemistry a lot. And so we use the chlorandic acid anhydride as both an imide protecting group for a terminal amine and an active ester protecting group for a terminal carboxylic acid. And as you can see, because now all products are crystalline and at the same time they're highly soluble in organic solvents, I'll comment on that on the next slide as well, we could perform easily in our regularly equipped synthesis lab these syntheses on the multi-dozen gram scale, even towards the final compounds. And we also made use of the same style of protecting group for the perylene bisimids, which we then could further functionalize. And so that gave us a toolbox of oligocyphene and perylene bisimid diamines and dicarboxylic acids for further functionalization. And as I said, all these compounds are nicely crystalline. Actually, they typically precipitate from the reacting mixture upon simple cooling after the reaction. And we believe that what is responsible for the high solubility combined with high crystallinity is just the packing of the molecules in the crystalline state that is somehow enforced by these chlorandic acid side groups, end groups, because they're much more bulky than the typical pi stacked pi conjugated systems. And so you see that the system actually resorts to a layered packing, which in the case of unsymmetric molecules is an interdigitated layer of molecules coming from both sides. But the next layer is held together with this one only by halogen-halogen bonds, which are easily addressed by a reasonably polar organic solvent. So they crystallize nicely, but at the same time they can be easily dissolved. And then the symmetric compounds, as you see here, of course an interdigitated packing in this case is not possible. And so some of the final compounds actually give up on pi stacking completely, not the ones I've shown here. Others, like this one, you don't see it in this projection, have solvent channels, solvate channels going through the crystal. So I believe that this is one other element responsible for the high solubility of these compounds. And as you see, in some cases, we observe typical pi stacking, either between the thiophene rings of the oligocyphenes or between the thiophene rings and the succinimidyl residues of the chlorandic acid residue. But in most cases, actually, we see other types of interactions that are dominant. For example, as I said, chlorine-chlorine interactions between the layers, or bromine-oxygen interactions within the layers. And so I think that this is kind of just a neat trick that made our whole synthetic pathway very, very convenient to pursue. Then we take these building blocks, for example, an oligocyphene dicarboxylic acid, and just link it in a final peptide coupling step to a polymer oligopeptide that we deprotected on the amine side, and we're done. And so as you can see here, we took the molecular parameters we previously determined, transferred them on this molecule. We still made a series of different molecules with differently long oligopeptide segments just to see what would be the effect on the self-assembly. And so after we had the molecules in hands, and after we had kind of a tool chest of molecules that we thought would be appropriate for self-assembly, we investigated the formation of nanofibrils in solution. So the idea is just that, just to repeat, that we would like to take these molecules, dissolve them in an appropriate solvent, a moderately polar organic solvent to promote strong hydrogen bonding. And the molecules would ideally line up as schematically shown here, with the aggregation strongly promoted by hydrogen bonding between the peptides, but at the same time the helical twisting laterally limiting the aggregation so that we don't see bundles. And from a variety of different characterization techniques that, again, time does not allow me to go into in detail, but I'll be very happy to answer questions about it. For example, solution phase IR spectroscopy, we could see that as soon as the oligopeptide segment was long enough, which coincided with our previous investigations on the diacetylenes, we obtain an amide A vibration, which is the NH stretching vibration, or also an amide 1 vibration, which is the CO stretching vibration, that is very sharp and can be interpreted as a highly ordered parallel beta sheet-like aggregation the way we wanted it to. And if you do this IR spectroscopy in solution temperature dependent, you see that there is a deaggregation temperature in the range of like 100 degrees centigrade. So the self-assembly process is actually thermally reversible and can be performed under thermodynamic conditions in solution. What you see in the AFM images that you then obtain as you take a solution and deposit a sample on a substrate is that if the oligopeptide segments are too short, so that IR spectroscopy shows it's non-aggregated molecules, you obtain drop-like features, so no defined aggregates of any sort. But as soon as the oligopeptide segment is long enough, you obtain very well-defined nanofibrillar structures, whereby well-defined means all of them have the same diameter, and in those cases where we can actually distinguish a helicity, all of them have the same kind of helical morphology as well. And this persists even at higher concentrations. So what happens at higher concentrations is you still do not form bundles. You may see that fibrils align close to one another, okay, by a weak penetration of their polymer shells. However, mainly you obtain the same kind of fibrils that are just crossing each other and form a random spaghetti-like network. If you take a closer look at the AFM images and vary a little bit the tapping conditions, you see that actually the fibrils have a rigid core with a height on the order of 3 to 5 nanometers that you can also distinguish very nicely in the phase images. And these 3 to 5 nanometers correspond very well to the oligopeptide, oligothiophenene, oligopeptide part of the molecule, whereas the soft material seems to be placed along the flanks of the nanofibrils. And we investigated all of this a little bit more closely with the help of a collaborator in Chemnitz in Germany who invented something he calls multi-set point intermittent contact mode AFM, so music mode AFM, to have a more catchy acronym for it. And so this allows you to obtain height and phase information at different set points in a single measurement run, so that you're not so much prone to imaging artifacts. And what you can see in these images is that the height image shows you periodic corrugations, which can be attributed to the helicity of the fibrils. In this case, the hydrophilic-hydrophobic contrast doesn't show very much, but the hard-soft contrast shows you that mainly the soft material shown in dark here is actually placed along the flanks of the fibrils. And I'll show you two more such images just to give you a complete kind of overview that this is kind of a universal scheme. So here we looked at a molecule that had a quadrithiophene, a tripeptide, and hydrogenated polyisoprene as polymer segment. We can change most of these parameters, so we can go to a tetrapeptide, we can exchange the polymer for polyisobutylene. Again, you can see very well-defined fibrils. In this case, even the conventional AFM image shows a nice helicity, same helical morphology for all the fibrils, and the music mode shows height corrugations and again soft material placed along the edges. And we can finally even exchange the core from a donor type molecule to an acceptor type molecule. And again, conventional AFM images show nicely defined fibrils, again with a helical morphology. And the music mode images in this case again show height corrugations. And in this case, the hydrophilic-hydrophobic image shows two lines running diagonal where the bumps are. And so one can tentatively attribute this to the hydrophilic contrast from the oligopeptide parylene bismuth oligopeptide segment, schematically shown here so that you obtain these diagonal stripes. And to conclude this story, this is really a universal method to obtain nanofibrils. Not in all cases are they as well defined as I've shown you. We need to work on that. These are very fresh results from a new PhD student in my group who sent me the results 2 days ago. So in this case, we exchanged the oligothiophenene core for certain other core elements which we want to use to tune the electronic properties of the nanowires. But you see that a little bit this will also influence how these guys self-assemble. So we need to play a little bit more with like thermal annealing in solution and the actual preparation of the solutions in order to obtain better defined nanofibrils in this case. Good. So I hope that so far I've been able to demonstrate that we have a very nice and universal method to obtain nanofibrils from pi-conjugated molecules with a defined superstructure formation. We understood, however, a little bit better what the internal structure is because we were able to prepare hierarchically structured microfibers from the nanofibrils that then allowed us to perform structural characterization a little bit more thoroughly. So in order to obtain the microfibers, we just took a solution containing the nanofibrils and injected them from a solvent into a non-solvent. By pulling out the needle here, you just see the tip of the needle of the syringe. By just pulling it out from the non-solvent, you obtain a hair-like object, which is centimeters in length and has a diameter on the order of a few micrometers, just like a hair. And at the same time, we were able to tailor the diameter of these microfibers just by using differently thick cannulas. So, for example, we could dial in, or here you can see it better, we could dial in roughly 6 micrometer, 10 micrometer, or 18 micrometer diameter microfibers. And these were highly aligned or internally highly aligned species, as you can see from polarized optical microscopy in diagonal position or in extinction position. Using a retardation plate told us that the fast refraction direction is in fiber direction, which by analogy to the literature tells you that the oligopeptide segments, so the side groups, are actually lining up vertical to the fiber direction. And accordingly, polarized IR microscopy shown here for the amide-2 band, the amide-1 band that I already referred to earlier, so the COO stretching vibration and the NH stretching vibration, shows a systematic variation depending on the angle of the polarizers of the IR microscope. And again, this tells you that because the CO stretching vibration is smallest in 90-degree position, this tells you that again the carbonyl groups are parallel to the fiber direction. The oligopeptides are thus perpendicular to it. I'll come back to that in a second. SEM imaging of the microfibers shows that they have some sort of a hierarchical structure with like larger bundles that are composed of smaller bundles. And if you zoom into these smaller bundles, so shown again here by AFM imaging, you can see that actually these smaller bundles consist of a highly aligned array of the nanofibrils that we had processed from solution. And so it is not a surprise that we get nice data from polarized optical microscopy and IR microscopy. However, more importantly, these microfibers then allowed us to do fiber X-ray. And here you can see in the small and wide angle X-ray region mainly 4 peaks. The least important one is the biggest one, which is just the near order peak of the attached polyisobutylins in this case. But then you see a 6 nanometer peak, which corresponds to the diameter of the closely packed nanofibrils. You see 4.6 angstrom peak, which is the typical, or a little smaller, I have to say, than the typical intermolecular distance in beta sheet-like systems of oligopeptides. And you see the 3.4 angstrom peak that one can assign to the pi-pi stacking inside the nanofibril. Here you see the azimuthal distributions of these 4 peaks. Sure enough, you see that the nanofibrils are aligned parallel to the microfiber direction, as are the polymer chains that are kind of sheared along the shearing direction when we prepare the microfibers. Interestingly then, the oligopeptide distance spacing is oriented at 90 degrees and 270 degrees, so again showing that the oligopeptides are actually oriented perpendicular to the fiber direction. And the pi-pi stacking distance has an azimuthal angle at 48 degrees, or consistent with a conical distribution of the parallel bismuths in this case, with an angle relative to the fiber axis of around 48 degrees. And this is trigonometrically very consistent with a picture that looks like this. So if you have a stacking distance of 4.6 angstrom of the oligopeptides, an angle of the parallels of 48 degrees with a microfiber axis, then the pi-pi stacking distance that you derive from that trigonometrically is 3.4 angstroms. In the case of the oligocyphins, it's 3.5 angstroms. And so that is very well consistent with the data we actually obtained from the X-ray. Okay. Now, what is remarkable about it is actually how close it is. Yeah, so 3.4 angstroms you do find in parylene bismuth single crystals, but it's actually already very close to the interlayer distance in graphite. And 3.5 angstroms for the oligothiophenes is much closer than what is typically observed in polythiophene such as P3HT. It is as there are a few examples of similarly tight pi-pi stacked species in the literature, like certain almost monodispersed short oligomers of polythiophene that have shown a similar distance. So overall, I hope that I've been able to convince you so far that we have a very simple molecular design for molecules that then form nanofibrils by a combination of pi-pi stacking and hydrogen bonding. And the way we've built these molecules, including a small flexible spacer between the pi conjugated segment and the hydrogen bonded segment, actually allowed these two supramolecular interactions to enhance one another rather than impede one another, despite the fact that they have two very different characteristic spacings of 4.6 and 3.5 angstroms. And because of that synergistic enhancement of pi-pi stacking with hydrogen bonding of the lateral substituents, we observe a very tight pi-pi stacking, which persists, or so we hope, in the nanofibrils that we then characterized because we were able to make these hierarchically structured microfibers. As I would like to demonstrate you in the following, this tight pi-pi stacking has profound consequences for the question of interaction of the nanowires with light and the question of charge carrier generation. So let's first take a look at the optical spectra of our molecules, both the aggregated ones in solution and non-aggregated molecules that so without an oligopeptide, that I will always use as a reference in the following slides. As you can see here, the non-aggregated molecule have a UV vis absorption peak with a maximum at around 400 nanometers, as it is typical for molecularly dispersed quarter-thiophenes. The aggregated molecule, however, has a peak dramatically blue shifted, much narrower, and with a certain let's say fine structure that we are now pretty sure is not a vibronic fine structure but results from something else. At the same time, the CD spectra of the non-aggregated molecules show no CD activity, so the molecular chirality of the molecule is not sufficient to induce a CD activity in our case, but the aggregated molecules have a very well-defined CD band, with a bisignet band with a zero crossing at the position of the UV absorption maximum, and a positive Cotton effect that one would ascribe to strongly interacting quarter-thiophene cores stacked in a p-helical or right-handed helical fashion. I'll skip over the fluorescence data for now, but I would like to point out that we did extensive the structural information we had from X-ray allowed us to perform molecular dynamic simulations in the group of Clémence Cormenboeuf, who then took snapshots of the molecular dynamic simulations that she obtained and performed DFT computations of the optical spectra. And the optical spectra she obtained in this case look like this. So we could reproduce the three bands that we observe in the experimental spectra, which is a weak red-shifted band, a main band that is blue shifted compared to the monomer absorption, and also a third peak in the middle that we named a monomer-like transition. So what that means is that the fact that we see these three bands is a result of the specific geometry of the nanofiber as we obtain them. The fact that we still see a shoulder at the position of or roughly at the position of the monomer doesn't mean that there is an equilibrium with monomers, with non-aggregated species. It's more like there is temporal vibration-like disorder in the stack of the oligothiophenes that gives rise to this band. But mainly, we see an H-type aggregate, which results in the blue shift, combined with a weakly allowed J-type transition due to the specifics of the geometry inside our nanofibrils. More specifically, if you look at the positions of this blue shifted band and the red shifted band by means of DFT computations, and you perform a scan of how the two different bands, so here's the blue shifted component, here's the red shifted components, vary as a function of the displacement of two neighboring oligothiophines relative to one another along their long axis X, their short axis Y, so in these directions, and also the Z direction, so the actual spacing, you see that we are in a, or we can only reproduce the experimental spectra very well if we assume that the Z direction has a spacing on the order of 3.5 to 3.6 angstroms. So this coincides very well with our X-ray determinations, and with a longitudinal displacement on the order of 2.5 angstroms, that's roughly one thiophene ring, and a lateral displacement that is pretty much non-existent, that is negligible. So we have an in terms of lateral displacement, an almost cofacial stacking with a bit of longitudinal displacement at a very tight pi-pi stacking distance of 3.5 angstroms. As a result, preliminary transient absorption spectroscopy data suggests that there must be an additional pathway of excitation decay. So here you see a non-aggregated molecule versus an aggregated molecule, and you see that after the initial excitation, the peak decays relatively quickly into what is a triplet state of the molecules. In the aggregated state, the spectra look different, and we don't know what is the reason for that in detail, but more importantly, the excitation decay is much faster in the case of 1 as compared to 2. And secondly, the intensity of the final triplet state species that is formed due to excitation decay is much smaller. Please consider that the axes are actually different in this case. So how we interpret that is that there must be, after initial excitation, an additional pathway for decay. We could so far exclude that it's singlet-singlet annihilation or energy transfer. So we believe it's charge transfer, the nature of which we're not entirely sure of as of yet. But I will comment on that a little bit more in detail at a later point. Now, importantly, as I already mentioned from the IR spectroscopy, the aggregation in solution is thermally reversible. And this you also see in the UV-Vis and the CD spectra. So you take a solution containing the nanofibrils, and you heat the solution, and you convert the H aggregate peak into the molecular peak, and you cool the solution again, and you go back. So everything is nice and thermally reversible. But what we noticed at the same time is that in addition to this main UV-Vis absorption, we see two additional bands of relatively high intensity compared to any other system in the literature. So this is about 1/10 of the height of the main optical absorption. In the red and near infrared region. And these peaks are actually typical for a quarter thiophene radical cation. And as you can see, these peaks actually completely disappear as we heat the solution and deaggregate the nanofibrils. And as we cool the solutions and reassemble the nanofibrils, these peaks slowly come back up, even in the dark, even under careful exclusion of oxygen. As you can see from those series of spectra already, the disassembled molecules do not show this. The non-aggregated molecules do not show this, nor do I know of any other example in the literature where a quarter thiophene has shown as spontaneous, quote-unquote, radical cation formation in the absence of an oxidant. Sure enough, these bands are the result of a radical cation. So if we take our original solution, we add a reductant, we can quench them. If we add an oxidant, we can reestablish them. And we also observe the same bands in solid films of our material that have been carefully kept under argon. We have then investigated what could be the generation. We excluded oxygen. We tried our best to exclude other inadvertently present oxidants. And we then found that actually these peaks are generated in a light-induced process. So as you take a solution that has been just cooled so that the nanofibrils form, but not given a lot of time yet, then you see, and you expose it to white light, then you see that these peaks actually drastically increase in intensity, whereas they increase much, much slower if you keep it in the dark as well as possible. If you then, as you then switch off the white light, the intensity of the signals decays again, but as you can see here, the decay is actually very slow. So this is a time frame on the order of 1 week until it finally returns to its final state. So, I think we can say we have a surprisingly long-lived radical cationic species that only, probably due to some follow-up chemistry, then slowly disappears. Sure enough, if it's a radical cation, it should also show an ESR signal, and it does. And so, whereas the non-aggregated molecule shown in black does not have an ESR signal, our aggregated molecules in the nanofibrils show a nice ESR signal both in solution and in solid films, shown here with a Gauss factor of 2.0024, which is typical for a quarter-siphene radical cation. It's also close to the free electron frequency, and at a surprising density of overall 3.6 times 10 to the 16 per cubic centimeter. Now, if you consider the fact that probably the polymer part and the oligopeptide part are innocuous, so it's only the quarter-thiophenes that are responsible for that radical cation formation, this actually translates into a spin density on the order of 10 to the 19 in the quarter-thiophene part, which is 2 to 3 orders, well, actually 3 orders of magnitude higher than what is observed for polysiphene materials under similar conditions. Again, the ESR signal can be quenched with a reductant. It can be reformed adding an oxidant. We tried to exclude the role of the chlorinated solvent by going to methyl cyclohexane, but we also observed the signal in the solid film. So we're pretty sure it's actually an inherent feature and not a result of some oxidation process, not even involving the chlorinated solvent. As we did the ESR spectroscopy in solid films, temperature dependent, you see the original spectra here, and as you plot the doubly integrated ESR line as a function of temperature, which is a measure for the paramagnetics, the ESR accessible paramagnetic susceptibility of the system, you obtain a plot that looks like this. So in a low temperature regime up to 60 Kelvin, we observe a 1/T relation, which can be attributed to Curie behavior of localized spin carriers. So in this case, in this low temperature regime, this means that we're actually dealing with localized radical cations the way an organic chemist would draw them. But then we switch to another regime that looks like it's weakly thermally activated. And so this actually suggests that here in this temperature regime, the spin carriers become mobile. And consistent with that picture, a plot of the line width as a function of temperature shows a consistent decrease in line width over the whole temperature range, which can be ascribed to motional narrowing. Now, as we plot our data, according to different models that assume localized charge carrier species, for example, variable range hopping following Mott's equation, we obtain typically good relations, but we obtain at the same time physical parameters that are physically impossible. For example, in the case of Mott's equation, we obtain a delocalization length on the order of microns, which is just impossible. So it just shows that this variable range hopping model, or any other localized charge carrier model for that matter, is probably not a very appropriate description in our case. This can also be seen from the fact that if you do an Arrhenius plot of our data, again we obtain a good relation, albeit over a relatively small range of physical values. But we obtain an activation energy which is 6 millielectron volt, which in this case I would say it's not physically impossible, but it's actually very small compared to typical polysiphene materials, which is more on the order of 50 millielectron volt or higher, probably even rather like 200 millielectron volt. So we have an only very weakly thermally activated process. And so this is what makes us believe that we have a charge carrier mobility that is on the border between localized charge carriers, for example, following a hopping mechanism, and a very narrow band-like conduction mechanisms. And a similar borderline case has recently been reported for carbon nanotube networks, where people have fitted similar ESR data as we did, using Anderson's model for motional narrowing combined with a hopping wave function, which was then termed Wilson's model. And again, if we fit, we actually get a nice fit. The parameters we obtain, you obtain different time frames out of this data actually fits to the data reported in the literature. But again, we have a very low activation energy that coincides pretty well with the activation energy we observe from the paramagnetic susceptibility data. So that is where we are. What we believe is happening, and here we come back to the charge transfer process, is that upon initial excitation, the excited electron is transferred somewhere, quote unquote. To me, the most likely culprit is the carbonyl functions of the oligopeptides adjacent to the molecule that could be reduced to a ketyl-like species or something like that. And we believe that what helps us in this case is that the DFT computations have shown that between the blue shifted and the red shifted transitions, there are two other transitions that are totally dark, so there is no probability for return to the ground state once you enter these transitions. And we believe that there is some way of funneling the excited electron into one of those dark states, where they then have sufficient time to do follow-up chemistry such as a reduction. In any case, it's once again a universal process, so it's true for all donor molecules. So, for example, here I show you all three donor molecules I've shown you before. Again, they can be disassembled and reassembled by simple heating in solution, like the molecules I've shown you before. And all three of them show long-lived polaron-like species in the near-infrared region. What is interesting to us here, and we don't understand the details of these spectra at all, I have to admit, is that the different molecules show very different properties in terms of the broadness of the peak, which would, if it's a polaron-like level, kind of translate into the broadness of the polaron-like bands in the middle of the band gap of the material in the aggregated state, whereas others are very narrow, but on the other hand, very intense. So I hope that we can exploit this. How about acceptor molecules? Well, these do not spontaneously form radical anions, because they would need an electron from somewhere, and there is no reducting species anywhere to be seen in these molecules. However, in this case, as you can see here, this is a cell we made for doing UV-Vis NIR spectroscopy on thin films where we can expose it to vapors. And as you can see, of course, we can generate radical anions of these molecules by exposure to hydrazine, and if we then open the chamber to air, it goes back. And so I think we can exploit this, although I have to say that in this case we haven't made the control experiment with non-aggregated molecules at all. So far everything is nice, and I would even say remarkable, and we understand many things pretty well, but we don't understand one detail that I would like to expose you to. And this is, if you go to the molecule that is achiral, where we replace the alanines that we typically use with simple glycines, the IR spectra shows that the molecule more or less on a local scale assembles in a similar way. So we obtain a nice beta sheet-like band of a highly ordered aggregate. The UV-Vis absorption spectrum shows a maximum at virtually the same position. So we seem to have H aggregates in this case as well, but notice the absence of any structure in this case. However, in the absence of chirality, the molecule of course doesn't make fibrils. It makes more like monolayer films. The height of these films corresponds to the diameter of the fibrils we typically observe, but we have lateral aggregation into these film-like structures. Nicely enough, we see kind of a sergeant and soldier effect. So as we add 10% or 30% of the chiral molecule to the system, we go from these monolayer-like films to undefined fibrils to actually pretty surprisingly well-defined fibrils. But what struck us is that if we leave away the chiral component entirely, we do not observe any formation of the radical cations. So there is a topological effect that we do not understand very well in play here. It's not only important that the pi conjugated segments inside the nanofibrils are closely packed, which I hope I've been able to convince you that they are. It's also important that they're helically packed and that somehow this core of the nanofibrils is surrounded by something else. Yeah, it seems to me that it is like this. If we add 10% of the chiral molecule, then we're back to a situation where we can form the radical cations by exposure to white light, and the intensity of that peak actually scales with the amount of chiral additive we add. So far for charge carrier generation. In the last 5 minutes, I'll quickly show you our results for conductivity of the system. So for this, we mainly built 2-point devices where we evaporated gold contacts on top of a very thin film, a sub-monolayer film of our nanofibrils. Here, for example, showing the device with a 5 micrometer channel length. We tried to build transistors, and they showed some conductivity, but they did not show a gate effect, which, if I'm optimistic, I can say, well, if there are already all these charge carriers present in the system, it's probably not a surprise that we cannot use the gate to induce charge carrier formation. But we actually did observe macroscopic conductivity as soon as the channel length was 5 micrometers or below, which is nice in the sense that it actually correlates to the length of the average length of the microfibers, which is on the order of microns. So what it means to us is that actually charge transport is possible if a single nanofibril is contacted by the 2 gold electrodes, but it becomes impossible if the charge has to hop from one nanofibril to another one. The observed currents on the order of nanoampere may seem small at the beginning, but I need to tell you here that we actually counted from the AFM images the number of fibrils between the electrodes, and it's roughly 100. Even if it were 200 or 300, it wouldn't really matter. It translates into current densities that are actually exceedingly high inside the nanowires, on the order of 10 to the 4 ampere per square centimeter. And then we could actually fit our conductivity data for different devices with different channel lengths with one comprehensive model, the Fowler-Northeim model, which assumes contact resistance limited injection into an organic semiconductor. And from the high voltage branches, we could come up with a lower estimate of the mobility inside these quarter-siphon nanowires on the order of 0.12 centimeter square per volt second, which compares to some of the best values reported in the literature for quarter-siphon single crystals. We also tried to do the same with the Parylene system, the acceptor system, but in this case I already showed you that we did not observe radical and ion formation spontaneously. So here you see the 5 micrometer channel length device. Here you see an AFM image of the channel with the nanofibrils running here. These are the gold electrodes evaporated on top. So in this case, we observed in the absence of hydrazine, we observed virtually no current at all. So the scale here is a little small. I'm sorry for that. This is on the order of amperes, so there is no current. But as soon as we expose the system to hydrazine vapor, we actually get decent current voltage curves, which in the case of the 5 micrometer device seem to level off at about 10 nanoampere for 20 volts source drain voltage. The 2 micrometer device shows an almost contact resistant free current, but in this case we have to work on this experiment a little further because we're not entirely sure that there is not gold that is actually spanning the channel. We need to make sure that it isn't. And then finally, with the Parylene system, we then also were finally successful with building transistors. In this case, we used commercially available bottom gate, bottom contact transistors with interdigitated source drain electrodes, and we just spin coated a nanowire film, a dense nanowire film on top, and we obtained decent transistor characteristics, as you can see here, the output curves, the transfer curves, and a first lower estimate of the mobility, the electron mobility in this case, inside these perylene nanofibrils would be on the order of 10 to the negative 3 centimeters squared per volt second, which I find is a decent value. But again, these are very fresh results from the beginning of this week. So I hope that indeed I've been able to make the full circle, starting with synthesis and the molecular parameters needed in order to assemble molecules by a combination of hydrogen bonding and pi-pi stacking, so that you obtain well-defined nanofibrils with a defined with defined lateral dimensions, and more importantly, a very tight stacking of a single stack of pi conjugated molecules at their core. I hope I've been able to show you that this is then responsible for the unprecedented formation of long-lived radical cation charge carriers in the absence of a dopant, and that these can then be attributed, or that the macroscopic conductivity observed in these cases can be attributed to those systems. This is my last slide. You may ask, is this relevant or not? To be honest, I don't know. I think it's a study that elucidates charge carrier generation and transport under nanoscopic confinement. Whether this is useful for devices per se, the nanowires, I mean, I don't know. Probably it's much too much work. Probably there are too many parts in the molecule that do not contribute to conduction. However, I would like to show you one slide about another project in our group that would give rise to a whole new talk. I would like to show you that you can apply the same principles once you understood the role of hydrogen bonding and pi-pi stacking. Connecting a hydrogen bonded substituent to the pi conjugated core via a short flexible spacer. So we made these very simple small molecules that crystallize very nicely into a layered structure with a herringbone packing of the pi conjugated segments, very similar to the ones you know from the parent quatercyphene, or also alpha omega dihexyl quatercyphenes. However, the lattice parameters are roughly 10% smaller in all directions. Supposedly because the molecules are quote-unquote stitched together by lateral hydrogen bonding. And in collaboration again with Clémence Commenboeuf doing DFT computations, we have been able to show that this leads to improved pi overlap. And not only that, it also helps to grow very nice and large domains of the molecules. And as a result, we obtain in this particular case a mobility on the order of, I'm sorry, this should have been 1 actually, on the order of 0.45 centimeters squared per volt second, which to those of you who are actually into those numbers, you will say, okay, that's still not a good performance compared to other types of semiconductors. But mind you that this is 3 times higher than any other value reported for quatercyphene-based systems in the literature. And I have to admit that we're really not experts in device making, so I would consider these devices highly non-optimized. And still, the effect of local structure and also more thin film morphology helps to improve performance. And I think that this is something that needs to be exploited much more in the future. So I would like to thank the guys that are responsible for the project, which is mainly Liang-Fai Tian, who has done all the work on the quatercyphenes that I've presented. He just defended in April and now does a postdoc in Germany. This is Roman Marti, who is responsible for the work on the perylene bisimids. Jan Brauer, who does all sorts of spectroscopy for us. Lucia Hartmann, who is our electron microscopy and force microscopy expert. Michael Scher, who helped us with device manufacturing. He's an engineer with 48 years of working at EPFL. Imagine this. So I would not have been able to start this work without him. A number of collaborators, the guys in blue, actually contributed to the project. A number of funding agencies, and of course, I need to thank you for your attention and also for your patience with me being 5 minutes over time. So. And some cultural trivia at the end. This is our campus, which is extremely nicely located at Lake Geneva. You see the French side, the high Alps, the highest mountain in Europe, Mont Blanc, is over here. So that's very nice. But the problem is really the density of buildings. So we have literally no trees, and this is what I enjoy about your campus here.
Well, I would personally trade the trees for the Alps. Okay. I think you'll have an easier time remodeling the campus to put some trees in
Mm-hmm.
than we would to be on the
Build the Alps from concrete, you mean? Yeah, okay.
It's my own personal opinion. So with that, we'll open the floor to questions. Does anyone have any questions?
The spin densities in the self-doped or whatever, oligotypes, you gave a number in terms of electrons per cubic centimeter. What does that work out as in, holes per quantifiable unit?
Mm-hmm. It's it's something that I forgot to mention, or maybe I didn't mention it because we're entering the realm of speculation here. There is an interesting relation to helicity, and maybe this is where this chiral-achiral thing comes into play. It's actually one spin per 120 molecules, which means one spin per 60 nanometers, which happens to be very close to the helical pitch. It's roughly one spin per helical pitch.
And you're assuming that all of the ESR signal is due to the oligothiophene cations, whereas if you've got a ketyl or something somewhere else, presumably that could also be
Yeah.
region, right?
So I've only shown the region of the region of the spectra that is kind of assigned to the region where you would expect a quarter-thiophenene radical. However, I can assure you that we made very broad scans and we did not see any other signatures. For example, we cannot find the radical anion, and we don't see any kind of triplet signature either. So yeah. So we tried our best to kind of find other species, but there is none. So what you see there, in fact, is the quarter-thiophenene radical cation.
Lava.
So in the experiments where you put the fiber between the electrodes, do you see a difference if you do experiment in dark and under the light?
This is a very sad story because we need to redo the experiments. Initially we thought we did, and you would expect that you do, but we could in fact show in control experiments that what we saw was really just photoelectric effect from the gold electrodes. So we saw an increase with light, but it is really just the gold electrodes and photoelectric effect in vacuum. And we need to redo the experiments in a better way. I don't know whether we would have to use other electrode materials or something like that. So I haven't, had you seen my talk 3 months ago, I would at the very end have shown you a nice slide where you can see, like increase of intensity with light, but increase of current with intensity of light. But unfortunately, so far, we did not do this experiment in a good way.
Other questions? I have a couple of thoughts, one of which is probably pretty far out. Did you ever consider the fact that, let's assume you had an electron on the ketyl, that it's hydrogen bonded, and
Delocalized.
that is extremely delocalized, and that the mobility of your system is actually being determined by the cation following a very highly delocalized anion around. And that might also be, I don't know if the anion is so delocalized, whether you would see it by ESR or not.
It should actually be the other way around.
Yeah.
It should be the other way around, Seth.
Wouldn't get broader?
It would narrow. Yeah, it would narrow due to motional narrowing. And so what we actually assumed was rather the opposite, is that we don't see the radical anion because it could be in the same region where we see the other peak, but it's so broad that we don't actually see it underneath. That's what we assume. But your thought is still interesting because I was discussing this with Richard Friend, and so he believes that the high spin density that we see and the fact that we only see it in the helical system is first of all because we if you think about it as a core of the quarter-thiophenes surrounded by an oligopeptide shell, roughly a core shell structure. Yeah, okay, it's helical, but roughly it's a core shell structure. You generate these anions in the shell, which shield the charge in the core. And this might be the reason why it's only possible in the nanowires and not in the films of the achiral molecule. And it might also explain why we can generate such a high density of them. That was his thought.
But you don't think that You don't think that the system is delocalized?
It might be delocalized, but still not mobile. You know, the question is, why do we see this, and why has nobody? People have made quarter-siphene carboxylic acids and esters and the like, but they have never reported this. So the question is, why do we see it? And I personally follow your line of thought, and I would think that due to the fact that the carbonyls are actually integrated into this hydrogen bonded array, this might give rise to a delocalization once they are reduced, and this might be the reason why their energy is so much, or the accessibility towards reduction is so much better than for other systems. I believe that could be true, but I have no means, or I cannot think of a good way of proving it. So it's speculation.
Do you see any change? I mean, it would not be trivial to do. Do you see any change in the IR?
We haven't systematically looked at that.
Okay.
We haven't looked at that.
This is a question for you. If it was delocalized, the hydrogen bonding was important, and you deuterated it. Okay. You're changing all the zero point energies of the hydrogen bonded candidates. Yeah. Okay, well, we can think about that offline. Any other questions? Okay, if not, let's thank Holger again.